So we'll start this lab session. So what we are do here is yeah. So in this you can see this PDF, right? The lab sheet.
Yeah.
All right. So the point is to study the frequency response. So the first part is to study about the transients of a series RLC circuit. So the transient means the very first effect of a sudden turn on or a turn off of voltage on a certain component or a circuit. So in this case, to simulate that a sudden turn on or a turn off of voltage, we use a square wave. So in this case, we see a square wave generator of 5 volts peak. So they say 5 volts and then minus 5 volts to show that it's 5 volts to the top and then minus 5 volts to the bottom. So it's 10 volts peak to peak and 5 volts just peak, running into a 330 ohm resistor, 2.2 millihenry inductor, and then a 1 nanofarad capacitor. So they want us to set up the circuit as shown here with channel 1 and 2 of the oscilloscope to measure the input and the output. Now, what is the input and the output? The input is the voltage across this square wave generator, and V out is the voltage across this capacitor. So we put the settings across as it is in this square wave generator, and then see 5 volts peak. So to do that, we get to Multisim. You can see this, right? The Multisim program.
Yes, sir.
Okay, so to add a component, you press Control W, and then add these resistors. So you put to add a resistor, you put RES, and then you have to select resistor rated. So what happens when you select resistor rated is that you can edit this value, the 330 ohm value. Same with L1, the inductor, Control W, inductor, inductor rated. When you put a rated, you can edit all these values. Same with the capacitor. Now for this thing, I use a square wave generator, so I told us to use a function generator. So you can find it on the right hand side here. The very first option is a multimeter. We're not using that. The second one is a function generator. And then we just place it like that. So in this case, I already have one placed here. I double click on this and then I go to the settings page. So for this experiment, we need a square wave as shown in this PDF, a square wave of 5 volts. So I put it to square. This thing has to be 100 hertz. And then this thing leave it at default, amplitude 5 volts peak. Then those are the settings for this function generator. And then edit these values of the resistor, inductor, and capacitor to fit this. And then we move on to fitting the oscilloscope. Similar to what we did to pick the function generator, we go down somewhere here, and there has to be an oscilloscope. I know it's right here, just below the wattmeter oscilloscope, and then we put it here. Now this is the thing where you have to be careful. So there are two channels, A and B, and each of them have two terminals, plus and minus. The minus for both channels is always a ground, and A and B you can select whatever wherever you want it to go. So in my case, I put A to be the input of the input voltage from this function generator, and then B to be the output voltage onto the capacitor. Now, when you run this thing, you will have an issue where you cannot distinguish both of these graphs. So because of that, even in the previous lab, that's lab 1, we had this issue. So you right click on this and click on segment color. So you put any color you want apart from red, which is the default color. So in my case, I put green. I think it was this shade. Yeah, this shade of green. So that's a green line. This is a red line. So you have to remember that red is from the source and green is from the output. So you open up the oscilloscope page and leave these two at the default values. It's fine. And then you run this thing and then you stop it. And then you uh, there's something wrong. Oh wait, it's 100 hertz. Yeah, even I did a mistake here. Make sure you set these units properly. Hertz, volts, peak. Rerun this thing. And then you scroll this thing to the start. Say it again, provide. Right. See, this is the square wave. This green color line. Yeah, that's what you call the square wave, our output. So they want us to, in the lab sheet, they want us to observe the input and output voltages on the oscilloscope and plot the output waveform on a graph sheet. So they told us to um, just take screenshots of this thing. Therefore, we have to go to this and then increase this time division until it shows like 2 cycles, and then take one screenshot here, and then also zoom into just the very start. There is this oscillation of the output, which is the green line. The red line is the input. The green line is the output. You take a screenshot of this as well. So that's the first step. The first few steps of this. Observe the input and output voltage on the oscilloscope and plot the output waveform on a graph sheet. And relate your observations to theory. So what is this relating the observations to theory? Since this is about circuit damping and transients, this oscillation is what you call an underdamped response. This oscillates like this because the entire circuit is not damped properly. If it was damped, the voltage across this capacitor should get to this red line like a gradual, like a slope, and then remain there without oscillating up and down. Because it's oscillating up and down, it's what we call an underdamped response. It's not damped enough to remain in a straight line. It eventually gets to a straight line, but then it's too late to call it a well damped response. So then you relate it to the observations on the theory, and the theory is there in the lecture note, the PDFs. It's lecture note 6, 6 part 1, all the way till part 7 or 6. And then we use that. And they want us to suggest a method to change the underdamped response to an overdamped response and a critically damped response. So what does that mean? So a critically damped response is when this point goes to the red line as fast as possible, but it does not bounce up and down. And a and an overdamped, sorry, that's a critical damped response. And an overdamped response is where it takes a very long time to get to the red line. So in that case, what you can do is you can just simply experiment with different values of the capacitance. So by default, this is 1 nanofarad. Let's put something like 50. What happens with 50? See, with 50, this thing gets slightly more damped than the other one. But then still, at this point, this green color line is above the red line, which is not damped enough. Let's put like 100 nanofarads and see what happens. I see. In this case, we can call this a critically damped response because it goes up here, it goes here, but then the green line does not exceed this red line. We always remember the red line is the input voltage and the green line is the output voltage across the capacitor. This green line does not exceed this red line. So that's what you can call a critically damped response. That's what we. So you can take a screenshot of this and then post in your Word document. And let's see what happens when you put this to like even more, like let's say 1,000 nanofarads. See, it takes a very long time to get to this maximum value. I mean, it's long enough so to even visibly fit the next start of the next block in the screen. So since we could have done the same effect earlier, as in we could have had this green color line reaching the red line with a smaller capacitor without without bouncing up and down. We can call this an overdamped response. This capacitor is overkill for this situation. We could have gone with a smaller capacitor and had a more a steeper slope, but yet critically damped. So what I mean is this: we can get to the red line faster, but not bounce along it. So if you put 100, like earlier, see, it gets there, but it doesn't bounce here. This is what you call a critically damped response. If you put 1,000, it doesn't bounce, but it takes so long. It takes a very long time to get to the red line. So that's why you call it an overdamped response. So that's pretty much it for the fourth part. And part one is complete. So any questions, guys?
So far, so good. It's okay, bro.
So okay, so part two, frequency response. So in this case, we have to do a few edits to the simulation. You take this off, delete the Y also, and then you set this to 1 nanofarad. Is it? Yeah, the default value 1 nanofarad, and then you edit this to make a sine wave, and then frequency is the same. Yeah, everything is the same. You set this to a sine wave. Now they want us to have two voltmeters for this. So control W, voltmeter, and there are four voltmeters: H, HR, V, and VR. So what does H mean? H means horizontal terminals, and then HR means horizontal terminals, but then it's the terminals are reversed. That means the minus is on the left side, plus is on the right side. In this case, the plus is on the left side, minus is on the right side. And then we also have V, and then and a reversed one. Minus is on the top, plus is at the bottom. So we choose this thing. This is a lot easier than the usual, the other three voltmeters. Is okay, and leave those two on either side of this. Similar to the previous experiment, we are still measuring the input and the output voltages. So this input and this is the output. Make sure the settings are fine, and then they want us to apply a sine wave. We set it to sine wave, and then an input frequency ranging from 100 hertz to 2 megahertz at 20 steps. So first of all, you need to make a plan for this as to what values, what 20 values are you trying to take. So to make this visually easy, it's best if you first print the graph paper and then get to solving it. So when you print the graph paper, why they say for every decade change in frequency is that from the from one step to another, from one major division to another major division, the frequency is increased by 10 times. That's why it's called a semi-log graph. So the very first reading, even if it says 100, the very first reading I took is 10 hertz, then 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, and then 1 megahertz, which is 1 megahertz, and then the next value 2 megahertz also at 20 steps. So when I did this graph, I made this Excel sheet for that. So this is what the graph looks like. Frequency, voltage out, voltage in, and then V out divided by V in. It's B2 divided by C2. Um, and then I took values. First, my first few values were 0, 10, 100, 1000, 10,000. Then I skipped here. These values were put in afterwards. 100, 1, and then 2. So these are the values I put for the few initial readings. So what you do is, if you want to select, if you want to start from, so I put these two first, and then frequency, I set it to, yeah, anyways, change in the frequency, I run the circuit, and then jot down the two frequencies, sorry, the two voltage readings. So for example, say that we want to measure it for 100 volts, you go to the simulation, sorry, 100 hertz, you set this to 100 hertz, make sure the frequency is set right, and then you run this. All right, first set this to AC. Yeah, set that to AC and then run it, and then jot down these two frequencies, 5.35 and then 5.35 on the Excel sheet. So 100, 5.35, 5.35. And since in the PDF they want us to find V out divided by V in, we set a different function for that. V out divided by V in. So V4 divided by C4. You get 1 for this case. Repeat it. So for the next step, we want to find 1K. You change the frequency 1 and then set this to kilohertz. Rerun it. and then jot down these two values, 3.536 and 3.536, right here, 3.536, 3.536, still one. Now you go on plotting, and then you will, what you will originally see is is a table like this: 0, 10, 100, 1000, 10,000, 100,000, 1,000,000, and 2,000,000. So you can see that in V out, at first it's constant, pretty much equal to V in, and then it slowly rises, and then there's a sudden jump at 100,000 at 14.534 volts. So these two 100,000, 100 kilohertz, stop it, and then run it again. See, 14.534. So because of that, we can say, because of this big jump in the voltage, we can say that the resonance frequency of this entire circuit is somewhere near 100,000, uh, uh, yeah, 100,000 kilohertz, 100,000 hertz. So far we have taken 1, 2, 3, 4, 5, 6, 7, 8 readings. We can afford to have like 12 more readings nearby these values. So because of that, I took those 12 readings on either side of this 100 kilohertz to increase the accuracy. So this is what it looks like. These grayed out readings are the in-between values. So 10 kilohertz all the way till 100 kilohertz, I put all the in-between values. And then from 100 kilohertz onwards, I put until 500 kilohertz those values, 1, 2, 3, 4 values. Yeah, after the resonance frequency, there's a big drop, a drop that's below the input voltage also. These are all being these are all important to having mapped onto your graph. So anyways, after you plot this thing, you get yourself a graph paper, and then a semi-log paper, and this is what I chose for the semi-log paper. Yeah, this is my semi-log paper. So 10, 100,000, 10,000, 100,000, 1 megahertz, and then 2 megahertz. Um, so yeah, that's about it for drawing the graph. And also for the y-axis, you have to put V out divided by V in, this value. And then for the x-axis, you put the frequency. They say log f, but then put just the frequency because we are already using a log graph. So by observing the plot, find the resonant frequency. What does that mean is that find the frequency with the maximum output voltage, which happens to be 100,000, sorry, 100, yeah, 100,000 hertz for us. So V out divided by V in value for 100,000 hertz, in my case, it happens to be 4.11. So we plot it there as well. And compare your answer with the theoretical value. So there's an equation for finding the resonant frequency of circuit. It's there in lecture note 7 of electricals in the course book. You can refer that and then find the theoretical value. Now they want us to change they want us to suggest a method to change the resonant frequency of the circuit. So what do we do to that? We know that what's causing the resonance is the capacitor and the inductor that's here. So since the output voltage is measured across the capacitor, we can see that changing the capacitance of this capacitor will change the resonant frequency of the circuit. So let's try it out. Let's put like 100 nanofarads. Okay. Oops. Restart. And then it shows a very small value here. Let's see what happens when you put like 10 kilohertz. See, that's a bigger value. Let's see what happens when you put 1 kilohertz. See, even bigger. Let's go to the hertz range. Mhm. See, we have a very different resonant frequency. Can't happen to find it. Let's
Yeah,
compare
so
this. Yeah,
shouldn't the capacitance be 1 nanofarad?
yeah. I edited. Yeah, it should be 1 nanofarad originally, but then I edited this value to show how changing this value will affect the resonance of the resonance of the circuit.
Oh, okay.
Initially, it was
Okay.
1 nanofarad, so and our resonance was 100 kilohertz. Right? See, we get 14.3534 volts here by changing this capacitor to a different value, even 10 nanofarads. See, this resonance is no longer there. The moment we change it to 10 nanofarads, the entire resonance is shifted to the left side of the spectrum. So that's what happens. That's the way to change the resonant frequency of the circuit. So yeah, that's about the entirety of the simulation. Any questions, guys?
So for that last question, the answer is like changing the capacitor.
Yeah, changing the value of the capacitance. That's right, guys.
Yeah, I just had to type the document. That's it.
Yeah. Also, the due date is on Friday, by the way.
Hmm.
We have that FDD thing on Saturday.
Oh, yes.
The, you're sure? No?
Yeah, thank you. Yes.
No worries.